Next up is titrations. We've gone over titrations from a real basic level before. We went over them in general chemistry, your first semester course. We're going to switch that up a bit. We're going to get a little bit more detail into what the whole process of a titration looks like. We're going to build off the foundations, though, that we started with last semester. So, for our acid base titrations, this is the way we want to think about the chemistry. There's a solution that contains an acid or a base. It could be a weak acid or a strong acid. It could be a weak or strong base. It just has an acid or a base in it. What we do, though, is we add to it a titrant. And that titrant is definitely strong, and it's the opposite behavior. So if we have an acid in solution as our analyte, we're going to add a strong base. If we have a base solution to start with, we're going to add a strong acid. So that's what I mean there. We're adding in a species with the opposite behavior. All right. We know from last semester that what you do with titrations is you keep adding until you see a color change, until you know the reaction is done, right? You use an indicator just like you did in lab. What you hit is an endpoint, right? The endpoint is the experimental, like, stopping point, right? You might see the word equivalence point. For us in the lecture, they kind of mean the same thing. Right? Equivalence point. They mean that in your addition, what you have is a situation where everything's been, right, neutralized, although we'll see that that doesn't mean that we get a neutral solution. All the moles of your starting species equal the moles of the thing that you're adding. So again, just to make sure you understand what the endpoint is or where the reaction stops, right, based off of what we know last semester. Say I had an acid to start with. I'm going to add a strong base. The reaction is done when the moles of acid that were in there to start equal the moles of base that you have added. Again, if this is confusing, go back and make sure you review your Gen Chem notes on titrations. What's new is the rest of the ideas that I have down here. What's really important for us is that when this occurs, when you have a starting acid and you do a reaction with a strong species, this strong species reaction is a full reaction. And so what ends up happening is if you get rid of all your starting acid, for instance, what you've created is the conjugates. So at the endpoints or the equivalence points, which are the same thing for us from a lecture standpoint, the conjugates have been made. There's a complete conversion of starting material to its conjugate. Okay? Those conjugates then control the chemistry and the pH at the endpoint, right? Just a quick little example here. So say I have a general acid HA. I'm going to add strong KOH to it. I'm going to draw a single arrow. Why? Because there's a strong species involved. This right here should look familiar from general chemistry. HA plus KOH gives me H2O plus Ka. All right? Now, we know from our arguments this semester that these Ks, they don't really have an effect on pH. They're just spectator ions. So maybe it's best to kind of think about it as, oh, if I'm really adding KOH, what am I really dumping in there? OH minus. That's the active participant in the chemistry of your solutions. All right? So really it looks like HA plus OH minus. The OH minus grabs this H. This is a super strong base. So it goes just in one direction completely to that side. We get water, and we get the conjugate, right? HA we started with, here's the conjugate base. To organize these ideas, we often use what's known as an if table, IF. The way that I do if tables is you put moles in here. You put moles in here, and you use the stoichiometry, and you figure out what's happening. So for example, let's say that we're at the endpoint. We don't have to be, but for this example, just to kind of show you how these works, let's say we're at the endpoint. Let's say we started off with 5 moles of HA to start. If we're at the endpoint, what did we do? We put in enough OH minus until there were 5 moles of OH minus. It's that idea of neutralization. It's the idea that you completely reacted your starting amount with whatever you dumped in there. All right? Water we don't really care about, again, all right, because it's not going to influence our pH. And we have 0 A minus to start. If tables are a lot easier than ice tables because you just kind of look and you make sense of it. Well, if I started with 5 moles of HA and I react in 5 moles of OH minus, how much HA is going to be left? There's a 1-to-1 relationship here. So there's going to be no moles of HA left. That's the whole point of an endpoint. It means that all your starting material is gone. Well, you put in the exact same amount from a stoichiometric standpoint, so all of this is gone. Well, there's a 1-to-1 ratio here. So what happens? All the HA disappears as the OH minus goes in, and it's all converted to A minus. So that's the important thing to kind of realize with an equivalence point now and an end point, all right? All you're starting, in this example, acid, goes completely to the conjugate side, right? Just to show you one other quick example with the opposite scenario. Let's say we had a base in there to start with, right? And we're going to think about getting to an endpoint again. So let's have this base. What are we going to dump in? We're going to dump in a strong acid. If I put in a strong acid, it's not going to be in equilibrium. There's going to be no K's involved. That strong acid is going to make, just like last semester, a complete reaction to the right-hand side. The base is going to pick up, right, the H plus. And then what you're going to be left with is Cl minus. Well, what do we know about HCl? It's a strong species. Does Cl minus even matter at all? Well, no. If I have this base and I'm adding a strong species, this conjugate is a spectator ion. It doesn't really affect the chemistry at all. So I can kind of get rid of it from both sides and focus in on the fact that if I start with a beaker of base and it's my analyte and I dump in HCl, it's really like I'm just doing a complete conversion to the conjugate acid in this case. Bottom example, we converted with our strong species to the conjugate base. This, we get a conversion completely to the conjugate acid. If I do an if table here, and let's say with the information of the problem, all right, I can find that I have, let's say, just like 2 moles of this to start with. At the end point and at the equivalence point, right? We don't have to be there, but just to, like I said, solidify the idea. How much H plus have you added? Well, you've added the stoichiometric amount. You've added enough to do a complete reaction. There was no conjugate to start. These go away completely because you put in the right amount. And how much conjugate have you made? You've made just the same amount in terms of moles as your original species. Now, last semester we called these neutralizations. Now we see these as conversions to conjugates. All right. Now, why is that important? Because we know that just because we're at the end point doesn't mean necessarily, in either case, that we're at pH 7. It means that we've made these conjugates. And we know that conjugates themselves, they could be acids or they could be bases. Okay? So we could have at the end point an acidic or basic solution depending on this behavior. Look at the top example. I start off with a base. I make a conjugate acid. The end point is going to have, in this case, a pH that's less than 7. Bottom example. When I do this complete conversion, the end point makes A minus. This is definitely a conjugate base. At the end point, my pH is going to be greater than 7. Okay? We can encapsulate all these ideas with what's known as a titration curve. Now, titration curves are going to have different forms based on the reactions, based on what you're starting with, based on whether all the species are strong or whether there's a weak species present, right? So we're going to go over a couple titration curves. We're going to go over the ideas, and it's about just making sure you understand where these ideas and where these forms are coming from in terms of what you'll see on the graph that we make. All right. So our first example, let's say that we start with NaOH, right? A strong base. And to that, I'm going to titrate with HCl. What a titration curve looks like is down here on this axis, you put milliliters of your titrant. Whatever strong species you're adding goes there. What you monitor here is pH, okay? Now, you have to kind of consider the chemistry to decide what the curve is going to look like. This chemistry, right, looks like you're going to get H2O in a strong reaction, because there's a strong species involved, plus NaCl. Well, when you go and think about this complete conversion, you generate H2O, which doesn't affect the pH, and NaCl. Na is a salt. Na is a salt that has an Na plus that comes from strong NaOH. NaCl is a salt that has a Cl minus that comes from strong HCl. These conjugates, right, of strong species, do they affect the pH? No. So when I convert them completely, when I do this reaction and I put in the stoichiometric amount of HCl, where am my endpoint going to be? Where is my endpoint going to be? Well, at the endpoint, I've just made complete NaCl. Does this affect pH? No. Conjugates of strong species do not affect pH. So then here's what the curve looks like. All right. We're starting with NaOH, so our pH is going to be above 7. So I'm just going to put a mark there. And what I like to do in my curves is I like to show where 7 is, because it's all about just that relative position. What happens is I put in acid. Kind of think about that if table, all right? As I put in acid, this is going to go down, right? As the reaction progresses to the right-hand side. The acid's eaten up by the base that's already in there. You get less basic, right? So as the reaction progresses, right? And for a strong species, we kind of draw it down there. For a strong and a strong, right? It's going down. The reaction is going to get more and more acidic. Eventually what you'll see is you'll see a drop in pH, and then you'll keep going. Where that drop in pH occurs, all right, at the middle point, now I didn't draw it perfectly, but at the midpoint of that drop in pH, this steep region, right, that's your endpoint. Now, for this example, why did I draw the endpoint directly on 7? Because I did that analysis previously. And what did I say should happen at the endpoint? Is there any more base at the endpoint? Nope. Is there any more acid? Nope. Everything's converted to conjugates. This conjugate right here, this does not affect the pH. So it gives you a neutralization, a true neutralization. It gives you a pH of 7. Now what you do for a pH curve is you keep going. So instead of just saying, hey, I'm done with the amount of NaOH and HCl was in there and making them equal, you keep going and you're going to get more and more acidic. And you just kind of pick up on, oh, well, if I keep dumping an acid, there's no more base in there to react. All the base is gone at this point. So if I keep going, what am I going to end up with? More and more acidic solution. Okay? This changes up in form if I would have, say, a weak base to start with. So let's look at that. If I have a weak base to start with, like NH3, for example, and I dump in HCl, okay? A full reaction occurs, and what do we make? NH4 plus, okay, NH4 plus, and Cl minus. NH4 plus and Cl minus. A full reaction occurs where the base picks up the H plus. Why is it a full reaction? We're dumping in a strong species. Okay. So what happens at the end point here? Well, at the end point, this is gone, and so is this. At the end point, what I've made, though, is NH4 plus. The Cl minus is still a spectator. So the NH4 plus is like the only species in there that's affecting the pH. This completely converts the NH3 to NH4 plus at the endpoint. So NH4 plus, what kind of species is it? It's a conjugate acid, right? And you know it's an acid because it comes from weak NH3. And we even did an example, I think, with it, where we could calculate its Ka based off of Kw and Kb for NH3. It has a Ka, it's a conjugate acid, it's a weak species, but it's definitely acidic. So imagine this. You have a base to start with, you dump in acid, right? But at the end point, you've made an acid. What does this curve look like then? Being different from our strong and strong situation, right? Two main differences. What we're going to get is more of a flat region up here, right? So the pH is going to be going down, but it's going to be going down slightly. And these flat regions become important. We are going to get a drop, all right? And then we're going to get a form like this. So you're saying, okay, well, what's different about this? The midpoint of this drop is the end point. And where is it now? Because we start with NH3. And at the end point, we've completely converted it to NH4 plus. Because the conjugate is acidic. Our end point is not at 7. Our end point is at a pH that's less than 7. So when we titrate a weak base with a strong acid, because we generate a conjugate acid at the end point's pH is less than 7. This flat region here will become important for us next week when we analyze it, but we're just going to kind of signify it now. This flat region is really important because we're dumping in strong acid, and there's not much change in pH. This region, which involves a weak species interacting with a strong species, is what we're going to call a buffer region. All right, a buffer region. So hopefully you can kind of see the pattern here. Let's change this up. And maybe you can predict, all right, what this looks like yourself. Pause the video once I set this up and see how you would think about the form of the pH curve that's going to sort of result from the reaction that I described. So let's say we start with something like acetic acid, HC2H3O2. That is a weak acid, right? And let's do a titration where we dump in strong NaOH, okay? Think about how you could analyze this, all right? Down here, we're going to put milliliters of NaOH, our strong species. If I just keep dumping in more and more NaOH, what do you think this curve looks like, all right? What's the end point relative to pH of 7, okay? So, now I'll give you the answer. Like I said, pause and try to figure it out. So this reaction is a full reaction because a strong species is involved. And what you're going to get is H2O and NaC2H3O2. So what you get is water and a salt, all right, as your products. But that salt, we know, could have acidic and basic properties. This salt is really Na plus and C2H3O2 minus. Well, hold on a second. That Na plus is a spectator ion. It really doesn't matter at all. It's coming from strong NaOH. So the end point, right, is all about making from our weak acid starting point. We've completely made the conjugate base. Okay. So this curve looks like we start with an acid when there's 0 milliliters of NaOH. Where's this pH going to be? It's going to be somewhere below 7. What happens is, right, we're going to raise the pH as time goes by, as our experiment goes by, because we're adding a strong base. So we're going to go up, we're going to get a flat buffer region again, right? And we're going to go up and up and up. And then eventually there's going to be a big flat region, right? Vertical region, I should say. And then This is going to taper off. Ooh, let me draw this better at the top. And then this is going to taper off eventually, right? Where's the end point? The midpoint of this vertical line is here. Now, why does this make sense? That this endpoint for this situation, where we have a weak acid and a strong base, why does it make sense that the pH is above 7? If I start with pure HC2H3O2, what have I made at the endpoint? I've made a base. Okay? So this really combines a lot of ideas associated with the behavior of salts, the behavior of conjugates, and the thing that's new is we can kind of track that behavior by dumping in a strong species, right? A strong species, right? I'm going to go over real quickly what you would see for like a polyprotic situation, all right? And I'm just going to do a general one, and then I'm going to kind of explain again one more time just to reinforce, all right, how you would look at this from the standpoint of, let's do something more simple. That's fine. From the standpoint of what this curve looks like, right? And I'm going to take phosphoric acid and I'm going to react it with NaOH, right? We know already that the Na is really not important. It's a spectator ion. So really it's like dumping in OH minus. So I'm going to make H2PO4 minus and I'm going to make H2O. That's the strong reaction that's occurring here. I'm starting with this acid, all right? I'm starting with this acid. And so I know I'm starting down here, all right? And down here I have H3PO4. So what I'm going to do is I'm going to do a reaction. I'm going to dump in NaOH. And what I'll see is I'll make a buffer region. And then I'm going to get a steep part. Now, this species we analyzed previously, right? And what did we find out about that species? We found out about that species that it acts like an acid. Its Ka was bigger than its Kb. So this endpoint is going to be here, right? So at this point we started with pure H3PO4, and right here we've made H2PO4 minus. Now why am I leaving more space here? Because this is an acid, and if we keep dumping in NaOH, guess what? Another reaction is going to occur. And H2PO4 minus, reacting with that OH minus we put in there, is going to make water and HPO4 minus 2. So we have three acid sort of protons, three acidic protons that we're going to be able to take off with this NaOH. So guess how many vertical regions we're going to see in our pH titration curve? We're going to see 3, right? Because you're going to keep going. This guy then can react with a strong reaction, and it can react with NaOH. And as I put in OH minus, it's eventually going to be converted completely to PO4 minus 3. So all that analysis that we did in terms of, oh, is this guy an acid or base? Is this guy an acid or base? It matters here and it shows up here in this curve. So rectify what I'm going to draw with what you know about each of these species. The more OH minus you put in, the more you're generating these conjugates. We started off with H3PO4. We're adding NaOH. We're going to have to get 3 different equivalence points because there's 3 protons to remove. After this first proton is removed, we figure out that this conjugate, because of our Ka and Kb analysis, it likes to be an acid. So where do we line that point up to? Someplace less than 7. This guy we found was a base, and so was this. So what we're going to get is another buffer region. And then we're going to get another vertical region. And this vertical region right here corresponds with making pure HPO4 minus 2. And then what are we going to get? I'm running out of room. More NaOH. And we're going to get another vertical region. And then we're going to get a flattening again. And what does this vertical region correspond to here? Making, or the making, of pure PO4 minus 3. Now, what's different about this curve? I'll just show you where 7 is. Because it was polyprotic. There's 3 different endpoints because there were 3 different H's to take away. You're going to see in your reading, right? What if this had 2 acidic H's? Guess how many vertical regions you would see? 2 different vertical regions. Every removal of an H in the strong reaction is another vertical region. How do I decide where these are lined up? You do that math that we went over previously. You look at this species and you decide whether it's an acid or a base with a Ka versus Kb check. And when you do that check, whatever you decide, in this case the Ka was bigger, remember we did that before, that tells you where you're putting the vertical region. I'm putting it less than 7 because it's an acid. When I did a Ka versus Kb here, what did we decide? The Kb was bigger. So where are we putting it? When we do the strong reaction, we take away an H, we take away another H. This species that we generate, we're going to put it above 7 in terms of its endpoint. Because this species we know is a base. Phosphate for sure is a base. There's no acidic properties there. There's no H to give away. Where is it? Well above 7. So pH curves associated with polyprotic species have multiple humps in them, right? Same ideas, all right, be able to interpret these curves. Same ideas for the simple curves. It's just, like I said, there's a little bit more to think about because you have to do multiple Ka versus Kb checks to see where these line up. But the ideas are maintained. At the endpoint, you've converted completely to a conjugate. You decide whether that conjugate is an acid or a base, and you line up the vertical region with that analysis, right? Or with the results of that analysis. And then you go from there. Knowing how to interpret these curves is incredibly important, all right? And in lab, if you're a non-major, you're going to do some calculations associated with these curves, okay? The regions that we'll care about next week, or the regions that we'll discuss next week, because it's incredibly important for biological systems, are these flat regions here. Each one of these flat regions is a buffer region, and it's good to know that this week that we call these buffer regions, but again, we'll figure out what that means next week as we discuss buffers as a whole.